So today I'm going to talk about big data, the big data platform at Netflix, and how we run it. It's a little different from most deployments and even a lot of cloud deployments. So I think it's a pretty good example of how we, or a pretty good example of how to do things. We're going to talk about HDFS versus S3 and the rename problem, and where that really trips up Hadoop, specifically in output committers. So I wasn't going to cover very much eventual consistency or things like that. I'm sure questions will cover it. All right, then we're going to talk about what we recently built, which is the S3 Multipart output committer that uses the S3 Multipart API. Then we're going to show some basic results, like what it benefited us, how it benefited us, and what needs to happen in the future. All right. So starting off with big data at Netflix, here are a couple stats for you. The main one is that we keep about 60 petabytes of data in S3. And this is data about basically everything that goes on at Netflix. A lot of people think of recommendations engines and things like that. But this is also a lot of telemetry from all of our runtime systems. So any system at Netflix providing some service, we have a lot of different microservices. They all log things. That eventually goes through Kafka, gets fed into tables that get compacted into Parquet and are available in our data warehouse. So we have a lot of data so people can do long-term analysis of how applications are performing over time, in addition to all of the other business use cases that you might be more familiar with. We read about 5 petabytes of data every day. Wow. And we increase by about 300 terabytes a day. We also have a big Kafka pipeline that ranges from 500 billion to 1 trillion daily events. And to process all of this, we have a ton of production systems, but on the big data side, we have 2 main clusters. We have a giant prod cluster, which is 3,400 D24XL nodes in Amazon AWS. And we have an ad hoc cluster that you can use for notebooks and basically development tasks. And that's about 1,200 D24s. Then we also have a variety of other clusters for different workloads. So moving data from Hive into Redshift or other applications that we use. Also, that compaction work that I was talking about earlier, going from row-oriented files into long-term storage in Parquet. So we have a ton of different clusters, and that's actually one of the key things about how we operate at Netflix. Clusters at Netflix are expendable. So we treat them like our other microservices. It's just more of a not so micro. So clusters are expendable. Whenever we need to update something, we bring up a new cluster, divert traffic over to it, drain the old cluster, and bring it down. So this follows the architecture where we can find a problem as we route traffic to the new cluster and route it back to the old cluster, which is how we run most of our production services as well. So anything that you need to do, if you need to change a configuration property that requires restarting all of the node managers, if you need to upgrade one version of Yarn to another, we don't actually do rolling restarts. We just bring up an entirely different cluster. And that's really, really nice because we don't have to worry about things like wire compatibility in Hadoop or Spark. We just bring everything up and call it good. And if you lose the name node, it's the same thing, but it's a bit more of a panic. So we also have, as a result of this ephemeral cluster architecture, a few changes. So you don't have a tier of nodes in your Hadoop cluster or your Spark nodes, however you choose to run it. Maybe it's Mesos. We don't have this tier where you SSH into to start applications. We have instead a tier of a cluster of computers that does job submission, and we call that Genie. So Genie determines what is the current production cluster and submits to that cluster. What is the current ad hoc cluster for your application and submits to that cluster. So that's how we do this traffic, pointing traffic to the correct cluster. So that is a persistent tier that we can also change at will. We also have a persistent metastore. So this single metastore contains all of the information about all of our data in S3. That's really important so that if a cluster goes down, we still have the metastore, and it's available across clusters. And the third thing that is necessary for this ephemeral cluster environment is keeping all of our data in S3. So rather than any data being stored long-term in HDFS, we use S3 as our primary data store, which has its challenges because, as you might know, S3 and HDFS are not really the same thing at all in terms of architecture. So S3, I like to say, is a object store masquerading as a file system because you don't get the same kinds of guarantees, and certain operations are just completely different. The one we're going to focus on today is that rename, instead of being a metadata operation that occurs just in your name node's memory, is actually a copy and a delete. So if you rename a file, whatever computer is renaming it waits for the data to be copied to a new location and for that to be ready, and then it gets notified that you're good to go, all the data is safe, and then you can delete the other file. And that's what happens under the hood. So the implication for this when we're talking about writing out data is that every output committer, or sorry, every file commit at the end of your Spark job ends it up being a rename operation that is then a copy and a delete. And that sucks because you're copying your data from a single node at the end of every job. And most of you that are using the output committer V1 API are actually doing that twice. That's really, really inefficient, and you're bottlenecking on a single node to do this. So in order to understand what we did and how we got around this problem, I think we need to understand what output committers do and what they're responsible for. So we're going to take the example of the direct output committer, which is the simplest file output committer because it doesn't actually do commits. So if you want to see the difference between a real output committer that makes some guarantees and an output committer that just kind of pretends, it's the direct output committer. How many people out there have used the direct output committer for S3? Seeing some hands, but most of them are coming up slowly. Don't feel shamed. It's not what this is about. But yeah, you should stop doing that. Okay, so we're going to take a look at what the direct output committer does and why you should use something else. And the reason behind that is that we tend to think of tasks like this. They're these tiny little machines that work perfectly all the time, except for when we have a hardware failure. But the reality is more like this. It's a whole bunch of children carrying around eggs on spoons, and we're racing them to the finish line. And it's just not all that reliable. Because anything can happen. Rogue parent comes out of nowhere, slaps the spoon out of a child's hand and breaks the egg. That's basically what happens when Yarn preempts your containers, right? Anything can happen. Spark might lose communication with an executor. If you're running 161, it's actually pretty common. 2.0 is what we had to move to in order for our Spark clusters to use dynamic allocation and be stable at anything past 500 executors. So that one was a big problem for us. Spark can preempt. Speculative execution is when you basically take two children, give them identical eggs, and tell them to race and push the other one out of the way at the end. Tasks might still run slowly. We could lose track of them, but they might still try to commit. They can do all these terrible things that we're used to in distributed systems. So in reality, the end picture is more like this. It's utter chaos, especially in a multi-tenant environment. So we use output committers to clean up this mess, to basically allow whatever's going to happen, but guarantee that only one attempt per task actually puts data in our final location. And once all of those tasks commit, we do some operation to make the entire data set live. So that's what the output committer API is designed to do. Just do whatever's going to happen in parallel and clean up the mess when all the tasks are done. So, to review, it guarantees one and only one copy of each task's output, and it guarantees all output from a job is available after the job completes, or none of it is. As you might have guessed, these aren't really guarantees because nothing actually does this. We'll go over that later and what you actually can expect from an output committer. So, going back to our example of a direct committer that just puts files in S3 and doesn't worry about it, what could happen? Well, two things. One, your tasks could just clobber each other, and you get, whatever data you get at the end. In S3, I think it's less of a deal because one version of a file is going to win, but it's still kind of a mess. And the main one here is that what happens if your entire job fails after some tasks have committed their data. So some files are live in S3. They're already showing up in your Hive tables because once a file shows up in a list operation, it's live in your data set. So if you have a partial commit, you have duplicate data at the end of your job. So these were actually removed from Spark 2.0. It's no longer possible to use the direct committers. And if you supply your own direct committer and Spark detects it, it'll warn you and say, that's a really bad idea. OK, so now we're going to go into the multipart committer. And to start us off, I'm going to go over a simplified version of what the commits actually mean so that we can think through this. So each task attempt, each task that runs, even if it's a reattempt or a speculative attempt, writes to a unique file. And then we take that output file once the task is completed, and we move it to the task output file. So in this case, we take temp task 4 attempt 0, and we move it to job 1, which is the job that we're completing, / task 4. So only one thing is going to be able to move a file there. The job commit is then to rename that temp job 1 directory to our final output path. And in a file system, these should be really quick operations. So moves are obviously supposed to be atomic, metadata-only operations. And this is kind of what the output committer does, the file output committer, but not quite. And remember, the move operation here, or rename, is not metadata in S3. So we're actually copying twice. Luckily, there's a way around this that we took advantage of at Netflix to build an output committer that doesn't have these problems. So S3 has an incremental upload API called the Multipart upload API. So it allows you, as your job produces data, it allows you to take chunks of that data, say 10 megabytes, and upload that to S3 and keep track of it with an ID. And when you're done writing the entire file, you take all of the blocks that you've uploaded to S3 and submit a final request that says, take these blocks and make them a file named whatever. OK. And the key thing here is that you notify S3 when you're finished adding blocks. And that's what makes the file live. So you've already uploaded all the data. You just have to notify S3. So using that, we created a file output committer. And what it does is it writes all of the data to local disk. So nothing is uploaded to S3. No files are live until the commit phase starts. So tasks do this upload. They chunk up the output file into blocks. They upload them to S3 using the Multipart API, and they completely prepare this notification to S3 that says, please make this file live. But instead of actually committing it and completing that request, they serialize the request and use a normal output committer in HDFS to send it back to the driver. So a normal output committer does the HDFS rename operation. It's a tiny file, and we basically don't care what happens. But some other output committer takes care of the fact that only one of those applications should commit. Then on the job commit side, this is what happens in your Spark driver. We read all of the task outputs. And having used the file output committer, we know that we have one and only one file from each attempt of a task, from each task that is completed. So we have that guarantee from the file output committer in HDFS where it actually works. And then we go through all of those pending requests and notify S3. We deserialize the request, send it off to S3, wait for it to come back, and then do that for every single file. So we have the guarantees that we wanted, which are one and only one file committed, and all of the data appears at the end of the job, or none of it does. Sort of. So while it will abort uploads and roll back, we are guaranteed only one file will be committed. It'll delete files if some of the requests to S3 fail. It's generally robust. There are still some failures that would cause this to have problems. So if your driver dies, gets preempted or killed by Yarn while your job is committing, it could have completed some of the files and not gotten to canceling or completing the rest of the files. So there is still a small window of time when your job might produce incorrect results. But this is actually what the file committer that most people are using anyway does, because it moves individual files into the final output directory. So it's actually much better than the current output committer, and we can do a little better through tricks to get around this job commit thing. Okay, so where are we now? We have a metadata-only job commit, just like the file output committer. Provides reliable writes to S3, unlike the direct output committer. Uses the entire cluster, or all of your tasks, to do the file uploads, which is the most expensive part. So we have distributed uploads and a very lightweight, or as lightweight as we can, job commit. And in our environment, this has shortened some of the job commit times by hours. Because instead of, for individual files, telling S3 to move from one location to another, and then deleting that, and doing that over and over again in a single process, we're just having this lightweight commit run. All right, so next I want to go into a bit of how you can use this, where's the code, etc. We've released in a GitHub project, which should be under Netflix, but it's actually under my name because I'm lazy. We've released a directory and partition output committers. So you can use these in your Spark job for any data other than Parquet by setting a Spark SQL property to set the output committer. I don't have that in the slides because we don't actually use it. What we do is we've gone into Spark and rewritten where it gets job output committers so that if it's an S3 path and we're using the file output committer, we'll just go ahead and use this new Multipart committer. That's to work around a Parquet issue where Spark wants all Parquet outputs to be committed by a Parquet output committer, which I think is a bad idea. So I would recommend people go in and actually change the way we did how Spark works, if you're running your own Spark distribution. Otherwise, you can just go and look up the property and set that, and for all non-Parquet Spark SQL writes, it'll work. In the long term, though, this is going to be included in the S3A file system itself. The Hadoop issue is up here, 13786. That's actually building it into the S3A file system so that the file output committer will detect, hey, this is the file system we're using. We should use something that is actually optimized for the S3 file system or S3 storage backend. And I want to give a huge thanks to Steve Loughran for really pushing this through. He took the code, he's been integrating the tests into Hadoop, and I haven't had to do a thing, which is really, I think, the best way to contribute to open source. No, seriously, huge thanks to Hortonworks for picking that up. All right. There is still some work to do here. Like I said, the Parquet output committers, Parquet file format wants a Parquet output committer so that it writes a special metadata file that is immediately out of date when you write any other data to this data set. So I think it's a mistake to do that, but we need to integrate this further into Spark and have a flag to turn that off. We'll probably be releasing a patch shortly to do that. In the long term, though, I'd love to talk to people after this talk and Q&A session about the Hive table layout. Because the fundamental problem here is that when you put data into S3 and those files can be listed in a table, they're immediately live in your data set. And that's a really poor way of doing things. What we should do is have a manifest of data that's in the data set instead of a manifest of directories in the data set. That would mean we wouldn't have to list thousands of directories in order to read data from S3, because we would have a complete list of files. We wouldn't have to worry about S3 consistent listings, because we would know all of the locations automatically, and we have read after write consistency. And just a whole slew of other problems would be fixed if we went back and fixed the table layout that Hive and Spark use by default. So with that, I think we've got about 8 minutes or so for questions. I'm sure I glossed over something, and there's plenty out there.
Thank you, Ryan. Well, we got 2 mics on either side of the aisle. We've got 8 minutes. Ask questions or?
The mic isn't on, I think.
It's coming to turn it on. Okay, meanwhile, I'll give you this one here. I'm going to digest my fruitcake.
So I was just wondering, for the Parquet side of things, is that a limitation in Spark or a limitation in the current Hadoop library?
Hear me?
Yes, now.
Yeah, that's a limitation in Spark. Spark checks to make sure the Parquet committer that you use is a Parquet output committer. It does that so that it can ensure that the metadata files are written, which is basically you take all the files that you wrote out, crunch down the Parquet metadata, and then stick that in a hidden file in that directory. And the reason they do that is so that they don't have as many operations to get the entire state of a table. But it all goes back to this problem where you have to list every single directory and read all of the files in order to have a consistent picture of a data set stored as files in S3. So we should just have a proper metadata store for that, and then we wouldn't have to worry about that problem.
Okay. So does this play into the S3 guard work that's going on as well in Hadoop?
Sorry?
Does this play into the S3 guard work that is also going on in Hadoop?
So yes, I think it's under that umbrella, but S3 guard, as far as I know, is a S3A implementation of something like Semper, which Netflix uses for consistent listing, and I believe we've open sourced that as well. And then there's one of those built into the EMR file system. And I believe Databricks has a version or some solution to that problem as well.
Closed source.
We need to give a chance to other people. Go ahead.
Hi. I have 2 questions. The first one.
Make it short, please.
Sure. So I always want to use S3 to save cost. So my question is about the streaming job. Have you ever used this in your Spark streaming job to save each batch output to S3 or checkpoint to S3? What are your thoughts about it? And then the second question is, can you share the situation when you decided to write your own committer rather than using the direct committer?
Yes, so I have not used this in a streaming case. I don't know exactly how Spark Streaming does its output commits. It may use a Hadoop committer for Hadoop file output formats, but I would have to check the implementation. My team primarily handles the batch side of things, although we do manage the Spark distribution for streaming. So I'd have to look into that. And your second question was on what made us want to do this. We've had something similar for a long time in Pig. So we have another output committer that uses the batch ID pattern, we call it, which is to add another directory level inside every single partition so that we can repoint Hive directories and make them immutable. So we do an atomic swap. We've had that for a while, but it didn't use the Multipart upload API, and we wanted to add append support. So in order to append to a live data set, you need something that's going to provide that at the end of the job, the guarantee that either all of your data makes it or none of it does. And while there's still a narrow gap of time, this is much, much better than just having tasks upload to S3.
You might have mentioned this, just to clarify, if we want to write out Parquet, we cannot use this solution in the near future.
So you have two options for it in the near term. The easiest one is probably just to go grab my code, change where all of my committers inherit from file output committer and they inherit from Parquet output committer. That's probably the easiest way for Parquet, and then set that property and everything should work. In the longer term, this will be built into Hadoop that gets into Spark. And if you do any of your own Spark branch management, like we pin to like Hadoop 2.0.0 and then backport things on top of that, and then package that up for our environment, because we have the ability to run multiple Spark versions on our clusters. So that's something that we get for free, basically, from how we deploy Spark. We just went in and changed the output committer logic, which I think is fairly easy to do.
Yeah, we're using EMR we get our Spark from EMR.
Oh, okay. Yeah, then that would be more difficult. So you probably want to use the first option, which is go change everything to inherit from Parquet output committer. That way that check works.
Go ahead.
Thank you.
My question is regarding the data integrity.
Could you speak into the mic, please?
Right. So since you are using S3 move and rename, right? So how do you ensure the data integrity constraint? Because move and rename is not atomic, right?
Right. This is avoiding using move and rename. So this uploads everything to the final output location instead. So where you would rename the file to, it uploads it directly there, but doesn't complete that upload or make the data live until the job commits.
Okay. Thanks.
We have time only for one more question, so go ahead.
So how do you compare your committer with Databricks' DBIO?
I don't know much about Databricks' solution. I think this is a pretty simple one that's open source. I know someone mentioned earlier that the Databricks one is closed, so I just don't know what it does.
If you do want to find out about the DBIO, do stop by at our booth, and we do have office hours this afternoon. People who actually implement it there will be there, so they should be able to answer your question to your satisfaction. Anyway, give a big hand to Ryan Blue from Netflix. Thank you.
Thank you.